So now I want to move over and look at Earth's structure and some of the physical features of Earth. So when we look at Earth, we talked about the core, the mantle, and the crust. But really what I want you to think about is we're going to think about it in two ways here. There's going to be some chemical, look at some chemical layers, and physical. So for the chemical, we're looking at remember, chemistry means there's a composition change, right? And so here we are going to have the crust, the outer skin of Earth. And remember, the crust will be divided into either an ocean or oceanic, which is a little bit thinner and a little bit more dense than the continental crust, which is our second one here. So thicker and less dense than the oceanic crust. And then we're going to have the mantle. So the mantle, in terms of the chemistry, it's going to have more magnesium and iron. So here, so Mg is a symbol for magnesium. We're going to have iron in here, right? But it's still a silicate rock, right? So you'll find that most rock-forming minerals are said to be silicate minerals. And you'll find when we do minerals, that's really the base molecule or structure for all the rock-forming minerals. When we look at the ocean and continental crust, up here the crust is going to have a higher proportion. There's going to probably be more sodium up here, more potassium, calcium, and silica. There's quite a bit more silica in the crust than there is in the mantle, although the mantle does have it, but we're seeing more magnesium and iron over here. And then we're going to have the core as our third layer here. And remember, the core is primarily going to be this iron, so Fe for iron, and nickel metal alloy. Now for the physical layers, we're going to look at it in terms of kind of boundaries. So we'll include the lithosphere. So we talked a little bit about the lithosphere already. So remember, the lithosphere is sort of a hybrid layer. It includes both the crust of the Earth plus the upper mantle, right? So the uppermost mantle. So those, remember, these lithosphere these are the tectonic plates. So when we determine the thickness of the lithosphere, we'll know the thickness of the tectonic plates. Now, when we get down here to the next physical layer, we're going to have another one called the asthenosphere. And the asthenosphere, well, this astheno here, this means, it's a Greek word which means weak. So a weak or debilitated layer. But this asthenosphere is basically non-Newtonian material. In fact, it's viscoelastic is the word we use. Viscoelastic. So when I say the word visco, I mean it can flow like a plastic. So it has a liquid property, right? Some sort of liquid property. But elastic, that means it bounces back, which is a solid property, right? So the asthenosphere behaves like a solid and a liquid at the same time. So it's kind of a strange type of material, a non-Newtonian type of material. And then when we get below the asthenosphere, we're gonna look at the lower mantle, right? And so the lower mantle is completely solid. It's again silicate rock, but with a higher percentage of magnesium and iron, and it's also going to be denser because it's under more pressure. There's more rock above it. And finally, we're going to look at our core. So here, the core. Remember, for the core, we're going to have an outer liquid core, and later on I'll explain how we know that, why it's liquid in the outer core. Temperatures are high, but the way earthquake waves travel through the Earth and give us information about the liquid nature of the outer core, and then we have a solid inner core. So anyway, those are our layers, physical and chemical. Now, looking back here, you can see that this describes some of those physical layers. So we have the lower mantle, which really extends from the base of this asthenosphere all the way down to the core. So it's a huge region. It's about 2,900 kilometers down there. And then the asthenosphere, and then note that the tectonic plates, which are the lithospheric plates, they're floating on this weak asthenosphere, right? So this would be like an ocean lithosphere here, and this would be continental lithosphere over here. So looking at the core, we'll see that the core ranges in density between 10 to 13 grams per centimeter cubed. We talked about inner and outer core, iron, small amount of nickel. The mantle, here they have 83%. I think I said 82% earlier, but usually I say about around 80%. So most of Earth, the most voluminous part of Earth is the mantle. It ranges from 3.3 to 5.7. So 3.3 would be up in the lithosphere, the uppermost mantle part of the mantle, and then 5.7 would be down in the lower mantle for the density. So again, solid, right? And here they say that the asthenosphere is partially molten. Well, maybe there might be pockets of magma, but it is, again, behaves like a liquid and a solid. It's viscoelastic nature of it, right? But it does flow plastically, right? And then we have this solid upper mantle lithosphere, which would be our uppermost mantle here. And the rock that's important here is peridotite. So peridotite is important for several reasons, and we'll talk more about those later on. But one is that it's a rock of the mantle, and it's primarily made out of a silicate mineral called olivine, right? So in fact, the gem variety of olivine is called peridot. So if you were born in August, peridot is your birthstone. And then for crust, we mentioned that there's ocean crust and continental crust. Note that ocean crust is going to be thinner and a little bit more denser than the continental crust here. Very thin skin compared to everything else, right? So the crust, for continental crust, maybe you're looking at about 35 kilometers thick, whereas ocean crust was maybe about 7 kilometers thick on average, right? So that's a little bit difference there. And then we talked about the lithosphere, and then an oceanic crust there as well. So what's driving plate tectonics? There's really three forces that's driving plate tectonics. The first is mantle convection. So there's three. There's mantle convection, ridge push, and slab pull. So what do they mean here? So if we look at this cross section of Earth, we'll see that this upwelling mantle. So think like a lava lamp. The light bulb heats up the wax gets less dense, and it rises, right? So warm wax, hot magma rising, and then that wax will cool and sink back down to be reheated again. So you get this convection cycle, which is a circular transport of heat, right? Moving in circles. So the fact that you're circulating here, you're going to cause that asthenosphere to flow. So that asthenosphere flowing causes the tectonic plates above it, the lithosphere, to move. Now, note that the mid-oceanic ridge here has a high topography above the seafloor. There's a gravitational push, which is pushing this whole lithospheric tectonic plate down, right? So that's that push, which helps move these tectonic plates away from that ridge axis. And finally, the third one, this slab pull. So once ocean lithosphere goes into an ocean trench here, into one of these subduction zones, the weight of this ocean slab, in fact, once it's subducted, we call it a slab. That ocean slab is pulling this tectonic plate, again, emphasized by this mantle convection. So we have the ridge push, the slab pull, and the mantle convection. Three basic concepts for plate tectonics. One is that we have these rigid lithospheric plates. So these tectonic plates are rigid, and they move. They're moving relative to one another, and we see that most deformation is going to occur along the plate margins. And then you'll see that those plate margins are going to be those divergent, convergent, and transform margins. So this is a drawing we saw earlier. You can see that the divergent boundaries are really where we see seafloor spreading, mid-oceanic ridges. We're generating new seafloor. So sometimes these divergent margins are called constructive margins. Subduction zones, is we're recycling the ocean lithosphere, the slab, back into the mantle. Sometimes these convergent boundaries are called destructive plate boundaries. And then there are transform boundaries. So you can see a transform plate boundary here where two tectonic plates are sliding past one another. Here in California, we have the San Andreas Fault, which is an example of one of these transform plate boundaries. The last part of the chapter discusses organic evolution and geologic time. And so fossils, they provide evidence of life in the past. And we see that life has changed quite dramatically in the last 542 million years. Darwin proposed this theory of organic evolution is that all living things are related by descent with modification from organisms that lived in the past, right? And that nature selects those individuals with the right adaptations or traits to reach reproductive age and have offspring. There's an equation I use for evolution, and usually I say that evolution equals traits, and these traits are adaptations, something that you inherited from your parents. So these are heritable from your parents, plus nature or natural selection. So here evolution equals the traits that you inherit that are heritable from your parents and their parents, and then nature or nature selects those individuals, and that leads to evolution. Right, so we'll have a whole chapter on Darwin and natural selection later on. So now, geologic time and uniformitarianism. So again, we call geologic time deep time because it's an immense amount of time that it's really hard to understand. But life and the Earth has changed dramatically in the last 4.5 billion years, and there are cycles. We've had ice ages. The Earth has experienced climate which is warmer than today. And we use a geologic time scale as sort of a timekeeper or a calendar that lets us organize events that occurred in the past, right, in Earth's history. And then so here's the geologic column, and you'll see that for the geologic column, we're going to separate the different groupings of times into eons, eras, periods, and epochs. So in lab this week, you'll be using these terms and understanding what they are. And then this other idea of uniformitarianism, well, this is one of the main tenets in geology. Because we interpret the past, we need to look at the present, because what this uniformitarianism, this principle, states is that the laws of nature, like gravity, conservation of energy, electromagnetism, the nuclear forces, weak force and strong force, they have remained unchanged through geologic time. Nature plays fair, follows the same rules today as it did 4.5 billion years ago. And so therefore, if we understand and are able to interpret geologic events from today, we can use that same understanding to place on rocks that we see in the past, right? So geologists must first understand present-day processes in order so that we can interpret the geologic past. All right, well, let's stop here for now.